So for this lecture, we are going to design a very arbitrary counter, and I will let you guys dictate terms here. I will let you guys tell me all the aspects of the counter except one. The one criteria is I want that to be a 3-bit counter. So we are doing a very generalized design counter design. So I'll start with the problem here. The problem is design a counter, design a 3-bit counter. That counts in the sequence now I want you guys to tell me the sequence. The options that you guys have are to pick values anywhere from 0 to 7. Doesn't have to be in that order. You can skip states, and some of them you can also skip, like you don't need to mention all of the 8 states. So what I'll do is this: to make it appear very, very random, you guys can take turns and put a number in the chat box, and I will take that as the counting value. But if there is a duplicate, then I will skip that. 5, 4. All right, 5, 4, 2 so far, guys. 5, 4, 2, 7. There's no 8. Why is there 8? So only 3-bit counter. Oh my gosh, 24. All right, I got 5, then I got 4, then I got 2, then I got 7, then I got 3, then I got 6, then I got 0. All right, let us skip one. Let's not have 10 of this. All right, so this is as random as it can get, right? This is the counting sequence that we are going to worry about. And I want this to repeat. So I want this to go back to 5, 4, 2, 7, 3, and so on, right? So I want this to kind of go in cycles. Pi. Now, since we have a 3-bit counter, I also want you guys to pick 3 different flip-flops, JK, D, and T. Which one do you want to use? Which one do you guys want to use for the most significant bit of the counter and least significant bit of the counter? So most significant, which one do you want? JK. All right, most significant bit of the counter, JK. How about the D is most significant? All right, all right, we'll use D for in the middle. How about that? And then we'll use T for the least significant bit of the counter. All right, I hope you guys are okay with this. So we are using 3 different kind of flip-flops to design this completely arbitrary 3-bit counter in which we are actually skipping one of the states. 1 is not included in this counter. All the other 7 are included. All right, so here, that's our problem. Step number 1. Step number 1 here is to draw the state diagram. Step 1. This will essentially help me visualize what my counter is supposed to do. And what is a state diagram? Essentially, it's a picture showing me what are the states and how do I transition between the states. That is it. So I have 7 states here, clearly. So 7 states. That implies that I'm going to need 7 circles in my state diagram. And I'm going to draw arrows between them to indicate state transitions. All right. So what did we have? We started off with 5, 4, 2, 7, 3. All right. So I need, first of all, I need 7 circles. So let me start with those. Let us use black for those circles. I hope I can do this. Okay. I got 1 circle there. 2, 3, 4, 5, 6, and 7. What? All right. So I got those 7 circles. Actually, I'm not happy with this. Better. What am I starting with? I'm starting with 5. So what I'll do is I will write 101 inside my state, and I'm going to call that state something, but that is 5. After 5, what did I have? 4, 2, 7, 3. 4, 2, 7, 3. What else? 6 and 0. I will also name them state 0, state 1, state 2, state 3, state 4, state 5, and state 6. Then I will use arrows to indicate how this transitions. So I've got 5 to 4 to 2 to 7 to 3 to 6 to 0 back to 5. And the thing to note over here is that the transition, when is that transition happening? The transition is happening at the active edge of the clock for the flip-flops. Transitions happen when there is an active edge. Active edge because it could be a positive edge, it could be a negative edge, right? Depending on the flip-flop. Active edge of clock. So for example, if I am going from state 0 to state 1, right, from state 0 to state 1, then this is going to be my, say, QA, QB, QC is going to become QA plus and QB plus and QC plus, right? So those are the transitions from QA to QA plus, QB to QB plus, and QC to QC plus. Those are the transitions that need to take place for your first counter transition from 5 to 4 and so on. You guys see that? Did we do the 5, 4, 2, 7 perfectly? 3, 6, yeah, 0. All right. You guys okay with how do you draw the state diagram? Pretty straightforward, huh? All right, so let's go on to step number 2, which is to draw the state transition table. Am I calling that? Yes. So step 2. All right, so for this, I'm going to start with my current state. Let me draw a big table here, right down the middle. Then I've got 1, 2, 3 for that, and then 1, 2, 3 for that, and then I've got Okay, I think this is fine. Now for the headings of the table, I would need QC, QB, QA. Why do I need 3 of them? Because it's a 3-bit counter, right? Those will transition to QC plus, QB plus, and QA plus after the active edge of the clock. Now I need to fill out what goes to what, right? And this is a table, so I need to talk about each and every entry here. So QC, QB, Q, let me also write this. QC, QB, QA are what? Current state. Current state of counter. And that is going to the next state of the counter. Let's fill in with all the zeros and ones. QC, QB, QA could be 0, could be 1, could be 2, could be 3, could be 4. Why am I doing it this way? 1 0 1 0 1 0. I think that's it. 2 zeros, 2 ones, and done. So those are the 8 possibilities for the current state. What is going to be the next state? Well, if you start with 0 0 0, what is the next state here? 1 0 1. Perfect. And after 1, what comes after 1? Don't care. Perfect. What comes after 2? After 2, we have 7. 1 1 1. And after 3, you guys know this. I'm just going to copy this and paste it over there. Copy and go next. Paste. And make it really small. I think that should do it. All right. So after 2, I got 7. After 3, what do I have? 6. Is this too small? Are you guys able to see this at all? All right. After 4, 0 1 0. After 5, 1 0 0. After 6, 0 0 0. After 7, 0 1 1. All right. How are we doing so far? Questions about how do you fill the current state and how do you fill the next state? All right, so it looks like you guys are doing okay here. So I don't need this anymore. So I'm going to get rid of that. And now I need to refer to the excitation tables, because I need to figure out what should be my input for the flip-flops so that I get those transitions to happen. And in our statement, we said, let us use JK for the most significant bit, D next, T next, right? So if you want that, QC is my most significant and QA is my least significant. I need JK to be for the most significant. So let's see. I'm going to denote that as JCKC. Right, for the C position, that's the most significant, I need J and K. Next, for B, we said we'll use a D flip-flop, so DB. And for T, we said, for A, we said T, so TA. All right. let me do DB first. What should I fill in for DB? The flip-flops are for helping with the transitions. You see, I need to transition from here to here to here to here, right? So the flip-flop, first of all, we have 3-bit counter, so I would need 3 flip-flops to do it. And my least significant flip-flop will need to be make that transition. My most significant flip-flop will need to make that transition, right? So the outputs of the flip-flops are essentially the value of the counter. Sierra says QB plus equals DB, and she is absolutely right. So all I need to do is I need to copy this column and paste it for DB. And I am done with that. All right, let's do TA next. Which 2 columns would I need to monitor to determine TA? Which 2 columns do I need to monitor? There are 2 columns here. Yes, QA and QA plus. Yes, absolutely right. So I would need to monitor this guy and this guy to fill in this guy. So let's see. 0 to a 1. Please toggle. 1 to don't care. Don't care. 0 to 1. Toggle. 1 to 0. Toggle. 0 to 0, don't toggle. 1 to 0, toggle. 0 to 0, don't toggle. 1 to 1, don't toggle. I hope you guys are okay with that. Now, we are left with JC and KC. Which 2 columns, actually, which 2 columns I would need to look at for JC and KC? QC, QC plus. Those 2 columns will determine both of those. Just for the sake of completeness, let's also do this. This column and this column gave us that. All right. Okay, so let's focus on the greens here. 0 to a 1. Well, I don't have an excitation table of JK handy. So what I'm going to do is on my screen, I'm going to pull up the, do we have it here somewhere? Let's see. If I go back here, I don't have it right there. I may have to go down a bit too further. Let's see. Flip-flops. And where is my JK flip-flop excitation table? Right here. And I can copy it from this place and come back to my counter design and maybe paste it somewhere here and make it very, very small. All right. So I've pasted it at the bottom. I'm sure it's not clear for you guys, but you know the idea. I'm looking up the excitation table of the JK flip-flop to do this. So the first entry is 0 to 1. If I want that transition from 0 to 1, I would need 1x. 1 0 or 1 1. Yes. All right, fine. Let's you guys are absolutely on top of this. 1x. Okay. What's next? 0 to x. Well, that would simply be xx. What's next? 0 to a 1. Well, 0 to a 1, we just did 1x. 0 to a 1 again. That's again 1x. 1 to a 0. 1 to a 0 is x1. 1 to a 1 is x0. 1 to a 0 is x1. And 1 to a 0 again is 1 to a 0 is x1 again. So I've essentially looked up the excitation table of a JK flip-flop to do this, which is right at the bottom here. Might be a little bit tiny, but I suppose you guys know what's going on here. All right. How are we doing here? Everybody okay with how we completed step number 2? All right. So the next step is going to be flip-flops. And our flip-flops are essentially going to be for finding the simplest expressions that will make our counter function the way we want it to. So step 3. We are going to use how many K-maps? Well, I need one for JC, one for KC, one for DB, one for TA. So I need 4 flip-flops, 4 K-maps. So I would need 4 3-variable K-maps so that I can write JC, KC, DB, and TA in terms of QC, QB, QA. And the idea is these 3 guys are inputs to the flip-flops, and these 3 guys are outputs to the flip-flops. Three flip-flops. All right, so let's do that. Let's do that on another page here. After current template. All right. What I'm going to do is I'm going to need to copy this. So let's copy this. And go up, paste, and minimize. And I'm going to put it over here, and then I'm going to start with K-map. K-map for, we'll start with JC. I've got 3-variable K-map. This is going to be QC, QB, QA. So QC, QB, and QA. 0, 0, 0, 1, 1, 1, 1, 0, and 0 and 1. And I'm doing this for JC. It's going to be 1x11, 1x11, xxxx. All of them are x. All right. So what is the simplest expression here for JC? 1. Perfect. Let's do next. What is next? Next is KC. KC, I need x, 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 1, 0, 1, 1. All right, what is the simplest expression here, you guys, for KC? So how about we do this? how about we do one group like that and another group like that. QA complement. Huh? Okay, QA complement or QB. That's what you mean. All right, let's see. So QA complement is good. And we have QB. Yes, you're right. All right, let's do this for next one. What is that? DB. What are the values? 0x111, 0x111, 2 zeros and a 1. All right. I thought we weren't required to cover all the x's. We aren't. We are just doing it to get the simplest expression. So you see, we left this guy out. So we use the x's only to make as big of a group as possible. That's it. Only if it helps you make a bigger group. All right, let's come back to this guy. What are we going to do here? My gosh, this didn't turn out very elegant, but let's see. No friend for this guy. And this guy can only go with this one, and this guy can only go with this one. I think that's it. That is all I need. So DB here is going to be QC complement and QB, or QB and QA, or QC and QB complement and QA complement. All right, you guys agree with this? This scheme map does. I know the last one. What do I? It's absolutely an arbitrary problem, you guys. Like we had no control over this. We did random counts. We did random. So this can happen. The only good news here is so far we have had unique simplest solutions, which is not always the case. So if there is a silver lining in this, that's it. All right, last one. TA. All right, for TA, what are you talking about here? 1x11, 0100. Better. All right. That's your group 1, and this is going to be your group 2. Again, a unique simplest answer here, which is very nice. So TC is TA is what? QC complement, right? Are we doing it correctly? QC complement, yes. Or the next one is going to be QB complement and QA. Well, I there was no way for us to do any different. All right, so are you guys okay with this step here? I suppose K-maps is very easy for you guys. So we have done the 3 variable K-maps. We got an expression for JC, KC, DB, and TA. Now comes the last step, which is to put everything together. So how many flip-flops do I need? Well, I need 3 flip-flops. So what I'm going to do is I'm going to arrange them as JC first. Sorry, the most significant flip-flop first. So I've got that, Then I've got another flip-flop right here. And I've got the last flip-flop right here. My first flip-flop is, well, they're all, let's suppose we have a positive edge triggered design, right? So our counter is, let's say, positive edge triggered. So we have got a positive edge for this, positive edge for this, positive edge for this. And that is going to be our clock input. So let's make our clock go through here. That's not nice at all. And connect all of them. So that's our clock. The outputs, well, the outputs are essentially our QC, QB, and QA, right? Those are the counter value. Then we have, for the first one, we have JC and KC. Then we have DB. Then we have TA. Now that our skeleton is done, by the way, we also have the complements, right? So for example, here, I would say Q and Q and that, right? So Q, Q and that, Q, Q and that, which I may use at some point. So this is going to be QC complement here, QB complement here, QA complement there. Now we go back to our expressions and we would connect the gates accordingly. So for example, what did we have? JC equals 1. Well, that was extremely simple. So we would say plus 5 volts, some pull-up resistor. JC is hardwired to 1. Does QC still correspond to Q0 when counting, or will it correspond to Q2 due to the way it was designed? So right now QC is our most significant output. You see, QC is our most significant output. QC, QC, QC. So QC has always been, since the very beginning, the most significant output of the counter. So Q2. All right, let's come back here. All right. How about KC? Well, let's look back. KC equals QA complement or QB. All right, so I would need an OR gate. Let us use an OR gate here, black. So the output goes into here. The two inputs are QA complement or QB. So QA complement is coming from where? From right here. And QB, right? QB, yes. QB is coming from right here. Now I'm just drawing this so that you can see the connections. However, just to make it seem a little bit more readable, what I would do is I would erase all of this and simply say KC over here, QA complement over there, and QB over here. But you guys know what those are, right? This is driving that, this is driving that, and this is driving that. And then similarly, you would have a network for DB and network for TA. So you would have more and more gates here that will drive the inputs of DB and TA, right? So you would need more things over here. But I suppose now it's just a matter of repetition. There's nothing very interesting happening there. But that when you complete that, that would have completed the design of our very arbitrary student chosen counting sequence, which is what? That 5427360. Now, when we come back in the next class, we will try to answer the question, what if our counter started at 1? So for example, as a power up state, if we had started at 001, where would this go? Would it go into the counting sequence? What would happen? So we'll try to answer the question of what would happen if our counter randomly powers up in one of the skipped states. We will try to answer that when we come back on Friday. So we'll use the same example. All right, so I hope you guys found that helpful. Questions about this? This is, will we have class next Tuesday? Oh, yes. Yes, we will have class next Tuesday. I can stop recording here.